in Pakistan now, in Islamabad. Right. So this is a class schedule. I revised it a little bit, and I sent you this file through the KakaoTalk. So you already have. So today, Fahim will introduce us about feature creation technique first part, and I'll be second part. And then Abi will lead us in discussion session. And next week we will have a midterm exam. Oh, I missed to send you the previous example. I'll try to do after the class, right? All right, let's start from Fahim. Do you have any question on schedule?
Okay, good afternoon, everyone. I am Fahim, and I'll be today's student lecturer. And the topic I'm covering is feature creation technique. So far we have covered the introduction of feature-based modeling, and we talked in depth about geometric modeling. Last week we covered feature concepts, and today we will talk about okay, so today's topic is feature creation techniques. There are 6 sub-chapters, and I will be covering the first 3, which are overview, interactive feature creation, and automatic feature recognition. So the total feature-based model can be considered of comprising 2 parts. One is the geometry part, and one is the feature part. The geometry model we've already discussed in depth about the BREF and the CSG type of models. And featuring is involving clustering of information, feature properties, relationship among information, and also higher level data than geometry. So feature-based models can be subdivided into 2 main categories, which are FFG and GFF. Can anyone guess what those mean, FFG or GFF? So FFG means feature from geometry, and GFF is geometry from feature. And FFG can be further divided into 2 parts, which is automatic recognition and human-assisted interactive recognition. So I'll be covering the FFG parts, and Professor will be discussing the GFF. From this diagram, we can simply see a relationship between the features and the geometry. Design by feature is the GFF, which makes geometry from preset features, and FFG makes features from geometric models. I think this image will better help you understand. So as I said, FFG is divided into 2, which is the interactive feature and the automatic feature recognition, and the GFF is the design by feature. So interactive feature involves first making the geometric model, and then as you can see, there's interactive graphic system, which is basically image of the part, and from there the user selects the features. For automatic feature recognition, it is pretty self-explanatory. The geometric model is made, and then the computer algorithm automatically recognizes the features. And for design by feature, the part geometry is created directly from the feature data.
Fine. Did you change the slide forward? I'm only looking at the content section, content slide. I'm looking only content slide.
I don't know, maybe it's internet problem again?
The sharing is not working well.
Yeah, it's slide number 3. Okay. 1 second, Professor. We went to call TA.
Go ahead while we are waiting. Go ahead, your lecture.
Yeah. The 2 FFGs and the GFF, the 3 main types of feature creation techniques can be further subdivided. And as you can see, that automatic recognition has a lot of sub-branches, all of which I will be discussing now. The first is interactive feature creation. So interactive feature creation was actually very old in that it used to provide feature data before design by feature and automatic feature recognition were popular. However, it is still used because of its simplicity. it can be used by recording pointers, and then you associate the parts with the feature name. And as I mentioned first, the geometric model is created, and then from the image of the model, you can label the parts with the feature. Furthermore, it can be augmented with attributes such as tolerances, finishes, and nominal parameters. The advantage of interactive feature creation is that it's very on the fly, as in users can use it for their specific domain of interest. However, there are many disadvantages, which is that the user is completely responsible for validation, and the level of information is very low. And also, the user is restricted to a predefined set of features. So there is lack of flexibility. I will show you a video to help you. Yeah.
Yeah, go down.
Down?
Yeah. No, in the middle, down. Yeah.
Oh, okay.
Sorry.
Okay.
Yeah.
So this is for interactive feature recognition in SolidWorks. As you can see, first he imports the geometric model into a graphical interface, and from this graphic of the part, the user will now, well, he's going to select, he already selected the interactive feature, and now he is manually choosing the part and then labeling the features. Interactive feature. And automatic feature recognition, as I said, is pretty self-explanatory, and I think we have all experienced in SolidWorks, is that the program itself recognizes the features from the geometry model, and we don't need any user manual input. So automatic feature recognition can be divided into two subgroups: is machining recognition and predefined feature. So the main difference between these two is that the machining region recognition does not compare the features to any predefined set of features. And as you can see, there are three subsections for machining and two subsections for the predefined. The first is machining region recognition. What it does is it generates numerical control toolpaths directly from the CAD database. And it does so by determining volumes that need to be removed from the part via machining, such as end milling. As I mentioned, there is no comparison to a predefined shape. So the first type of machining region recognition is sectioning. What this does is it divides the main part into part volumes. They are sliced with planes parallel to the XY plane at fixed delta Z positions, which are the tool positions. So they're used to generate feature boundaries at Z levels in, for example, 2.5 diameter milling. And once the part volumes are made, they result in intersection profiles, which represent the part's boundaries. These profiles can be classified as either material or void, and offset curves are then generated to form the basis for cutting if there is a void or material. And this sort of sectioning recognition is used in rapid prototyping, such as 3D printing. Second is the convex hull decomposition. This one, as Professor mentioned in previous lectures, that the convex hull of an object is the minimal convex volume that completely encloses the object. So what this does is it decomposes the volume into convex machining volumes, and then parts are subtracted from the convex hull until each part is equal to its own convex hull. This was originally, the original algorithm was designed by Tony Wu, who is currently of University of Washington, who is currently the VP of Nanyang Technology University. However, his original algorithm had the problem of non-convergence, and we got volumes that did not represent common manufacturing features. Kim Yong-se then overcame that problem of the algorithm by partitioning of non-extremal faces. These images will help you understand convex Hull decomposition. So first, as you can see on the left, the CSG tree nodes can be classified into the form feature model, which shows both the positive and negative, like the parts to be total shape. And then from this form feature model, we extract the machining feature model, which makes it easy for the machine to cut. However, there are many problems with convex Hull decomposition. It has multi-step reasoning, because first we have to generate the CSG tree, then we have to do the form feature recognition, and then from there we extract the machining feature recognition. Also, the CSG tree generation stage is separated from the feature recognition, and it is not guided by recognizing specific types of features. So that is another problem. Furthermore, success is not guaranteed, and it may also only work for polyhedron shapes. The third type of machining region recognition is cell decomposition. So this is similar to sectioning, but it is a spatial equivalent of it. What it does is there are three sets of planes which represent machining axis of three-axis milling machine, and they are used to partition and produce lattice of cubes. And it is this intersection of these cubes are then calculated between two values of 0 and 1. 0 values are classified as stock, and 1 values are classified as part cells. So it is the stock cells that are to be removed. Also, the cell size is determined by the feed amount of the machine. So we talked about machining region recognition, and this is the second type of automatic recognition, which is predefined. So the difference here is that the portions of the geometric model are compared to a library of predefined features. So properties are that it first searches for geometric models to match patterns, which are topological and geometric. It extracts these recognized features from the geometric model, and then it defines feature parameters such as hole diameter or pocket depth. And then it completes the feature geometry such as edge, face, vertex, and growing or closure.
Right. Right. Okay, it's better.
And then finally, we combine the simple features to get high-level feature data. So predefined feature recognition can be divided into two, which is boundary-based and volume-based. So first, geometric and topological conditions have to be satisfied and identified. And we have to search the model whether the conditions which are corresponding to each feature are first present. Boundary-based methods have three subclasses, which are rule-based, graph-based, and syntactic-based. And also there is sort of a fourth subclass, which is the neural net-based system, which is sort of a branch of rule-based system. It allows the probabilistic recognition of partial features that result from interaction of features. Okay. So topological conditions, we already know is that it means that the location of the feature. And first, we have to determine the number of topological entities and their adjacent features. But however, topological conditions alone are usually insufficient to determine what the feature is. That is why we have to use it in addition with material and geometric conditions. Material conditions mean solid sides or the void sides of the feature. And this involves measuring solid angles between faces, which can either be greater than 180 degrees, which is concave, or less than 180 degrees, which is convex. Also, another condition which should be measured is a geometric condition, which involves measuring the face type, which can be planar or cylindrical, and also the face orientation, which is perpendicular or parallel. So as you can see, these three different features all have the same topology because they are all one slot. They all have three faces, and one face is adjacent to two other faces. However, there are three different parts, which is obvious to us, but not necessarily obvious to a machine. That is why we have to combine with material and geometric conditions. However, for example, these two, even those are not enough because these two both have two faces, which are usually adjacent. They have a concave edge, which is V in between, and convex edge is X on the side. Therefore, we have to go further into this. For example, you have to measure the magnitude of the angle to determine what the feature is. So the first type of boundary-based feature, predefined feature recognition is rule-based recognition. What this does is it uses production rules, which can be seen here. So it's a condition which says that, okay, if the topological, if it satisfies some topological, material, and geometric conditions, then it is that feature. And to get the correct feature, a lot of trial and error is necessary to see whether the conditions are sufficiently met. This involves a very exhaustive search of a database, and therefore it can result in long search times for large and complex models. This is an example of the knowledge-based system or expert system. And as you will see later, the neural net is based off of this. The second type of boundary-based method is graph-based method. What this does is it matches the subgraphs in a solid model to graphs representing the features to be recognized. And it makes a separate data structure, which is called the face adjacency graph, FAG. In here, the node represents a face, and an arc represents the adjacency. Furthermore, geometry information, such as attributes of the arc, are also utilized. And arc attributes can be used to indicate when two faces are at concave or convex edges. There is an alternative of the graph-based method, which wherein the graph-based algorithm finds general features and uses rules to recognize very specialized features. So this is an example of a part, and it's FAG graph, as you can see. Two even this is not sufficient for example, these two parts here. That is why further division of the graphs is necessary. This is a subgraph for the through slot and the blind step. The third type of boundary-based recognition is syntactic pattern recognition, and this is adapted from the vision system. What it does is it looks for geometric patterns, which are described by straight, circular, or curved line segments. Also, it has language and grammar for describing the sequences in an algebraic form. Features are recognized by parsing the features against the description in the language and grammar. So, boundary-based recognitions are very popular, but they suffer from a lack of robustness in their algorithms, especially when feature interactions are involved. Feature interactions alter the topology, and they may result in the removing of some portions of features. An example is given, although I don't think it's very easy to understand here. As F13 is removed, for example, it would cause F9 to be divided into two phases. So these sort of feature interactions cause problems in normal boundary-based recognitions, and that is where the neural network comes in. What it does is it uses probability methods, and using weights for each condition, it can modify the rule-based methods to make them more robust. So this is just an example of one study which uses the neural network for flat-bottomed hole, and this is one of many examples. I think this paper was in 2003. Since then, there have been a lot more studies about using neural net. So it's a very popular method of feature recognition. And also, a neural net can be used for extracting data directly from the CSG models. And it can be, after some trial and error, it can be very accurate. After boundary-based methods, the second type of predefined feature recognition is the volume-based method, which is sort of similar to the machining region recognition in that it removes volumes. However, the difference from the machining recognition is that it involves extra step of classifying and matching the delta volumes, predefined volumes such as pockets or slots. So it produces and classifies the volume features from CSG or boundary representation, and it identifies the material to be removed from a stock part. So what a delta volume looks like is that it is classified according to the degree of freedom, and this then determines what motion is needed for the cutting tool to produce that volume. For example, if there is 1 degree of freedom, then it is a hole. If it's 2 degrees of freedom, then it is a linear sweeping. And if it's 2.5, then it's sweeping along a planar curve, such as a pocket. In this image, you see the stock model in part A, and part C shows the delta volume, the parts you remove to create part B. So to summarize, this is a graph of what we've done. So feature creation has 2 parts, which is GFF, which Professor will cover, and FFG, which can be further divided into 2 parts, which is automatic feature recognition and interactive feature creation. So interactive feature creation involves the user assigning features manually to an image of the geometric model. And automatic feature recognition has the computer program automatically identify features either by machining region recognition or by comparing to predefined features in a library. The machining region has 3 subparts, which is sectioning, convex hull, and cell. And the difference between the predefined is that they do not compare to a library of predefined sets. Predefined has 2, which is boundary-based. Boundary-based further has 3, which is rule-based, graph-based, and synthetic. And also volume-based. And yeah, I guess that's it for my presentation. Any questions? No?
You went to.
No questions.